Hey math people, we're looking at derivatives and integrals, so calculus, finally, of vector functions. So yeah, we're gonna just keep doing curves, right? We're used to curves on the 2D plane, we're looking at curves in space now. Can you do derivatives and integrals with it? Sure. The major application is gonna be within particle motion, but for now, we're just kind of defining some key moments. Yes, you can take the derivative, yes, you can take the integral, and then there are some other things. So starting with the derivative, there's the tangent vector and then the unit tangent vector, which are gonna be important. We'll practice that a little bit. We'll find some tangent lines. We'll kind of connect this to Calc 1 a little bit. We'll do some important moves that'll be a little more useful in the next two sections, and then we can say, yes, you can do integrals. So remember, this video is for you, Tyler. And the point of that is, yeah, just go around, click through the video as you see fit. Use the timestamps, pause when you need to, be patient with yourself. Let's do some math. All right, so if you remember the limit definition of a derivative, it sucks. So don't do it. That's it there. Yeah, just do normal derivative stuff. You know how to find derivatives from Calc 1. Yeah, just do it. So like looking at the first one, this is the helix, right? You just take the derivative component by component. That's the big idea here. Same story for 2, just component by component. So go ahead and take the derivative of each of these. First one's just gonna be some basic definitions. Second one, remember your product, power, quotient, and chain. 3, 2, 1. So within the first, these are just definitions, right? Definition of a derivative of cosine is negative sine. Derivative of sine is cosine, and then derivative of the slope of 1t is just 1. For each of these, you needed the product rule for the first one, you needed the chain rule for the second, and you need the quotient rule for the third. So you can take derivatives of vector functions just component by component. All right, if you were to find r of t, this is known as the tangent vector, so formally defined as just the derivative of each of the components. Okay, that's different from the unit tangent vector, which is, well, you would just take the derivative of each of the components and then divide by the magnitude. What we do ultimately is we take that r prime and we divide by the magnitude of r prime. What that gives us is that at any moment on our curve, any time valued moment, we can then draw and extend out a unit tangent vector. The point being is you can kind of like pluck out, we like the idea of the unit vector, right? Because what that does is it takes the length of the vector and it forces it to just 1. Let's just say I'm only concerned with the direction as I travel along this curve. Then the unit tangent vector would just be like at this moment of the curve, I'm going in that direction. So I made a Desmos on this, and you can see here that I'm traveling along this curve, so I have some point which is sine k, k cosine k. There it is. I have some point as I travel along the curve, and then the unit tangent vector is the small purple line that is the direction in which I am moving in along that curve at that instant in time. So there's some utility to that. All right, so if I wanted to find the unit tangent vector of this helix, I was looking at a slightly different one. See if you can give it a go. So the idea is you're finding r prime, and then you're going to find the magnitude of r prime, and then just divide each term by that. 3, 2, 1. So r prime is, we already found it, negative sine, cosine, and then 1. If I want to find the magnitude, very straightforward because we have a Pythagorean identity embedded within it. So sine squared plus cosine squared, that's just 1. So 1 plus 1 is 2. So that's why we have this root 2 in front. So yeah, if we were to then be a little crafty about it, we would just take the position where we are along the curve and then add that direction vector as the unit tangent vector. We get such an idea. A little bonus, a little extra for that. But all right, we can also just find normal tangent lines and just come up with the equation lines. That's kind of what I did over here without unifying it. So I want you to give this one a go just based off your own intuition if you'd like. But here's the answer in 3, 2, 1. The idea behind it is pretty much what you would expect. I'm finding the tangent line at exactly 1 time value. So what I can do is I can find that location in space, that ordered triplet, by plugging in that time value into the original. So I did that right here. So I'm looking for 0, negative 1, 1. There, I'll go ahead and graph some of this as because it's satisfying to see some of it. So my point of interest is 0, negative 1, 1. And my space curve is a very goofy one, sine of e to the t, and then times pi, whoa, comma cosine of e to the t, multiplied by pi again, I guess, and then e to the t. So this is the curve. Actually, this is a fun curve because it's going to grow up exponentially, right? Let's see what this looks like from -10 to 10. What? Where'd you go? Too big? Sorry, I don't understand this. What? Yeah, it's just too big. Oh, okay. It's not that crazy of an idea. It's really just another kind of fun spiral. It's a little tighter, I think. No, it still has the same radius. Okay, it just grows in a slightly different pattern than T would, I guess. So yeah, I'm interested in this point right here, and I want to come up with the tangent line from this point. So what I need to extract is I need to extract the direction vector, and then I would utilize this point off the tangent vector. So how I found that was I took the derivative, so I found the tangent vector, and I plugged in 0. This is my direction vector. So then if I then slap them all together, so I took the point that exists on my curve at time 0, and then I took the direction vector, which I found by plugging in 0 into the tangent vector. I would get the following. I would get, I don't want to, yeah, I got to do it this way. So it'd be negative pi t, comma, -1, and then I guess plus 0 t, so no slope on that one, comma, 1 plus t. All right, here it is. You would end up getting the tangent line there. Okay, cool. All right, so we can connect the new to the old. You did tangent lines back in math in Calc 1. It wasn't that crazy of an idea. So what I want to do is I want you to try out the new approach one more time. So you're doing the same thing that we just did. You're finding your location at the desired time value. So in this case, it's 1. We're just doing it within 2 dimensions now, so it's a little more straightforward. And you're finding your direction vector. So that is plugging in 1 into your tangent vector. So you're plugging in 1 into r, plug in 1 into r prime, and then just slap it on into your what is this, vector equation of a line from the last chapter. Give it a go, and then we'll make a Calc 1 connection. 3, 2, 1. So we found our r prime. We plugged in 1 into r. We plugged in 1 into r prime, and there's the vector equation form of the line there. You did this back in Calc 1, right? So if you're like, whoa, this is like a different idea, but it's like somehow the same, and you're a little overwhelmed by that, let me connect the bridge. Let's just go back to Calc 1 real fast. We see that the x component is t plus 3, and we see the y component is t squared. So what I can do is I can set t equal to x minus 3 just by subtracting that 3 over, and then that would just enable me to plug in x minus 3 for t. And this is just the equation. I'm just coming up with the equation of the tangent line to this curve right here when it's in R2, when it's in 2 space. And you were absolutely a pro at coming up with tangent lines back in Calc 1. Remember, you just take the derivative normally, you plug in your 1, which is your slope, you get 2, and then you would just you would plug in your ordered pair thereafter. So I have a time value of 1. I plug it into the first to get my x component, plug it into the second to get my y component, and then I slap it into point slope. That is the same thing as this line right here. The problem is, though, when we jump into R3 space, slope doesn't cut it anymore, and we have to talk about vectors. Vectors are required for this course big time. So it's new but old but new, however you want to word that. All right, let's just do derivative stuff now. If you're kind of overwhelmed by the concepts, let's take a step back. Just do derivative things. Find r prime of 1, find t of 1, find r double prime of 1. You can take the derivative of a derivative. And then actually this is going to have some utility, finding the cross product of 2 like derivative ideas in some of the future sections. So feel free if you want to try some of these. This is the twisted cubic. I don't know. Sometimes we have something called the twisted cubic. Is this the twisted? Yeah, this is the twisted cubic curve. All right, give it a go. 3, 2, 1. In terms of like the rote practice procedure of it all, it's what you would expect, right? Derivative, plug in 1, nothing crazy. 1, 2, 3. If I want to find the unit tangent, I'm just plugging in my I'm just plugging in my vector r prime into the magnitude formula. So I'm just taking the square root of sum of squares. So I just took my 1, 2, 3, and I just, like I said, square root of sum of squares. You just get root 14, so 1 over root 14 of this expression. So this is now a unit tangent vector. It's a unit vector. If I wanted to find r double prime, I just take the derivative again. So you get 0, comma 2, comma 6. And this one's a little goofy. I found the cross product. So if you want to sit there and do the ijk 1, 2, 3, and then 0, 2, 6, and then just write it out twice, or do what you need to do to find the cross product. This is a cross product. We're going to lightly talk about what this means, or a variation of this expression in the next section. Okay, lastly, you can also take integrals. Last idea, you can also do integral things. So if you were to integrate your vector function r of t, it's just integrating each component piece by piece. Just like how the derivative was taking the derivative of each component, integral is just the integral of each component. So if I had r prime, and that's equal to this expression right here, and I also know that r of 0 is the vector 0, comma 1, comma 2, can you work backward to find r of t? Well, you can. You just have to integrate each of these so separately. And remember, when you integrate, you get the constant of integration, right? So you get that plus c. So utilize your initial condition to find what your c value would have to be for each of these 3 components. You were doing 3 separate integrals, and you were doing 3 separate hunts for 3 separate c values. So sometimes teachers will do like c1, c2, c3, and then solve 3 separate equations. Up to you how you want to do that. Here's the answer in 3, 2, 1. So I did exactly that. I took the antiderivative of 2t. I got t squared. I see that at time 0, my output's 0, so I'm just plugging in 0, 0. So I'm just getting a c1 of 0. Nothing crazy there. I did the same thing for cosine 2t. I just needed to use like a u sub or like an anti-chain rule kind of idea, and I got 1/2 sine 2t. If I plug in a time value of 0 and I set it equal to 1, well, then I know the sine of 0 is 0, so I'm getting a c value of just 1. And then the last one is 1/2 negative cosine. So negative 1/2 cosine plus the c value, so plus c3 I called it. So again, at time 0, my output's 2, so I had an output of 2, and I plugged in 0 for cosine. Be careful, because the cosine of 0 is 1, so I actually have to solve this equation. My c3 value is 2.5 this time around. So I need an initial condition. I need to know, at some time value, where's my ordered triplet, or where's the vector pointing toward at some time value. If I didn't have that, I would have my constants of integration, right? Okay, that's really it for now. We're going to utilize the derivative and integral through the context of particle motion soon. I'll see you then, though. Math on.